Okay, so we just determined how we can kind of do the KSP, how we can find KSP. Now we're going to kind of use the fact that we already know KSP and essentially figure out what the solubility is, which is basically all it really means is what's the maximum concentration that we can get of a specific ion into basically how do we get them to dissolve? What's the maximum it can be? And instead of having it in molarity, we're going to do it in grams per liter. So here it says the KSP for CaF2 is 3.9 times 10 to the negative 11th. Assuming equilibrium is established between the solid and dissolved CaF2, calculate the solubility of CaF2 in grams per liter. So the first thing you do here, we're literally going to do the same steps up until the very end. So the first thing we're going to do here is we're going to find the KSP equation. We're going to write that out. So that's going to be Ca plus 2 times F minus 1 squared. Okay? And then we're going to put in our ice table. So remember, they both always start out as 0 because we're going to assume that we just put in the solid and we let it see what dissolves. Okay? And if we're adding in this situation, which again, this should be a solid. Okay? So if we're adding in here, we're going to shift equilibrium to the right. So therefore, we should be adding x and adding 2x. So our equilibrium concentrations for Ca plus 2 should be x, and for F minus 1 should be 2x. Okay? So now we're just going to go ahead and put that back in to our KSP equation. And that's going to be Ca plus 2 and F minus 1 squared. Okay, so we're going to plug in everything we know. So we know 3.9 times 10 to the negative 11th is KSP. And then we're going to multiply this by x and 2x squared. Okay? So if we multiply that out, we should get 4x cubed. So the first thing I'm going to do is I'm going to divide by 4 on both sides. So x cubed is going to equal 9.75 times 10 to the negative 12th. And then if I take the cube root of that, I'm going to get 2.14 times 10 to the negative 4th. Okay? And since the other one's going to be double this, I'm just going to look at my calcium concentration here. Because that's going to be the 1x. That's going to be the minimum, maximum. It's kind of going to be what we kind of go off of. That's the minimum amount that we can get to dissolve. So that's going to be 2.14 times 10 to the negative 4th molar. Okay? So, if we're looking at the solubility of 1 liter, okay, our solubility here should equal X, which is going to also equal our concentration of calcium. Okay? Now, in order to determine the full solubility, we have to know what the molar mass is for CaF2. So this molar mass determining doesn't go away. So our molar mass is going to equal 40.078 grams per mole plus 2 times 18.998 grams per mole. Okay, so our molar mass is going to be 78.074 grams per mole CaF2. Okay, and remember that anytime we have a concentration here, this M means moles per liter. So we're going to go ahead and put that in moles per liter. So we're going to say it's 2.14 times 10 to the negative 4th moles. And we've already said we're in 1 liter, so we've got per 1 liter. Okay? We're going to multiply that. We're going to get rid of that 1 mole of CaF2. And we're going to convert that to grams of CaF2. So if we do that, we multiply our molar mass times 2.14 times 10 to the negative fourth, we should get that number. And if we round that off to two significant figures, it's going to be 0.017 grams per liter of CaF2. Okay, and that's going to be our solubility of CaF2. So we can both determine our KSP and our solubility using the solubility product equation. Okay, so we've talked about all this. What kind of effect does this have on anything? Well, it's very important that we talk about both of these things, because really what kind of plays a role in what you need to know for your future as a veterinary technician, you need to know about two different things. The first one's going to be the common ion effect. And here's the idea here. It's whenever a weak electrolyte, and remember, an electrolyte is anything that dissolves or partially dissolves in water. Okay? So we can be dealing with either a weak acid or weak base, or possibly a solubility situation as well. Okay? And a strong electrolyte containing a common ion are together in solution. The weak electrolyte ionizes less than it would if it were alone in solution. Okay, so the idea here is that most of the time, if it's a strong electrolyte, it's going to be completely dissociated in solution. Strong electrolytes completely dissociate when they're added to water. So they're going to be an ion of some sort. Does this make sense? So if they're an ion, they're going to be adding towards your product side of your equation, especially if we're looking at solubility. So therefore, it's going to shift equilibrium back towards the right, and therefore make more solid and have less dissolved. Okay? So the idea here is that the addition of Ca plus 2 or F minus 1 shifts equilibrium concentrations, which goes ahead and reduces solubility. So the general rule that we kind of associate with this is going to be that the solubility of a slightly soluble salt is decreased by the presence of a second solute that furnishes a common ion. Basically, if you add another ion in there, your solubility will decrease. Okay? The other major point is going to be solubility in pH, which is kind of what we've been doing this entire time, although we don't really consider it. We're doing that. And the general rule for solubility in pH is that the solubility of a compound containing a basic anion that of a weak acid. So that's why it's important for you to remember your strong acids that were given to you in Unit 6. So it's very important you remember those. Okay? Increases as the solution becomes more acidic. And this is very important to remember because you're going to learn later about how this applies to keeping certain things in solution when you're looking at doing analysis of urine, of different blood things as well. You want to make sure that things stay to a certain pH in order to ensure that things stay in solution so you can be able to get the proper analysis. If they fall out of solution, your machines and your instruments will not be able to recognize them. Okay, so here's an example. We're looking at, this is supposed to be solid, okay? So we're looking here, we've got PbF2, okay? So here, our F minus 1 is a conjugate base of a weak acid, okay? So, if we're looking at what F minus 1 would be the acid that would go with that conjugate base, it'd be hydrofluoric acid. Hydrofluoric acid, while super dangerous, is not a strong acid. So therefore, it's considered a weak acid. So our solubility will increase as pH decreases. Basically, as you add more acid, as it becomes more acidic, the solubility will increase. Okay, and that's indicated in this picture below here. Now, if we look at PbI2, I minus 1 is a conjugate base of a strong acid. That was hydroiodonic acid, and therefore that one, if you remember correctly, and also if you didn't remember, go ahead and check your Unit 6 notes because I promise you it's there. Hydroiodonic acid is a strong acid. So therefore your solubility is unaffected by the pH. Okay? As you can see here, we add more hydrogen ions, nothing really happens. You have the same situation you had before. Okay? So if I gave you a couple of examples. First one here. Okay? Predict which of the following will become more soluble when the pH of the solution is decreased. IKA becomes more acidic. Okay? So here, we write them all out in their equations. I say is the easiest way to be able to tell whether or not those are going to become conjugate bases of strong acids or conjugate bases of weak acids. So if we look at calcium carbonate, that's going to go back and forth to form Ca plus 2 aqueous plus CO3 minus 2 aqueous. Okay? That carbonate ion is a conjugate base of a weak acid. Again, if it's not one of the acids that I told you about when it came to strong acids, it's automatically a weak acid. So therefore, here our solubility will increase. So our solubility increases. Okay? Next one, we're looking at BaF2, solid. This goes to form Ba plus 2 aqueous plus 2 F minus 1 aqueous. Well, I already told you that this is going to be the conjugate base of a weak acid. So therefore, our solubility increases. Okay. So here's something else to remember here. Whenever you have this hydroxide ion, this just means it's a strong base. Okay, so whenever I see a hydroxide ion, what the idea here is it's going to combine with the hydrogen ions to make more water. If you have more water, your solubility will increase. So again, if I look at this one here, because again I have more water to dissolve more solid. If I look at this here, again, I automatically see this guy. I should know that my solubility will increase. And the final one is going to be AgCl. So silver chloride. That goes to form Ag+1 aqueous plus Cl-1 aqueous. Well, remember, Cl-1 is going to be for hydrochloric acid. This is going to be hydrochloric acid. It's one of our strong acids. So it's the conjugate base of a strong acid. Therefore, there's going to be no effect. And that's it for the entire chemistry curriculum. So what we're going to do next is I'm going to get another online lab for you guys for the types of equilibrium, probably looking at acid-basis equilibrium, okay? And then from there, we'll do another test, and then you'll have your final, and that'll be it for the class, okay? I'm going to be writing your test up in the next week or so hopefully you'll have that sooner rather than later. We can also do a Zoom session if you guys are willing to do a review for a final, okay? That'll be at the end of the month. Hopefully you guys are going to be good with this, and if you have any questions, please let me know.